person before moving to Toronto. And he's going to tell us all about this radio array out in Western Canada.
All right. Thanks, everyone. Since this is University of Toronto, you guys have probably heard CHIME talks before, but CHIME is a multifaceted enough project that I think everyone who talks about it talks about something a little different. So hopefully this will be different enough to be new. So before I start, I want to acknowledge the army of people that work on CHIME. CHIME is mainly these 4 institutions, and we have collaborators at these other institutions, about 100 people in all. CHIME is a flagship project, I would say, for Canadian astrophysics. Here are some articles from mostly the Canadian press when we had our first light in September. Just between you and me, first light for a software telescope means that you change focus from cabling stuff to debugging. So even though we had our first light in September, we're still in sort of an engineering and commissioning phase. So I want to start by just talking about the basic idea of CHIME, which is to get a lot of statistical power at very low cost. So here's CHIME, and here's a traditional radio telescope, a feed suspended above a big dish. And the way the traditional radio telescope works, if there were only one feed, is that the focusing would occur by optically. So the geometry of the dish is constructed so that all of these paths have the same length. And so you get constructive interference if the rays are coming in from one part of the sky if you're in focus, and from a different part of the sky, the constructive interference condition would not be satisfied. And the idea of an interferometer is just to get rid of the dish and simulate it in software instead. So what I mean is you would, instead of having a dish, you would just capture and record the electric field at many locations, spaced by roughly a wavelength, and just combine those digitized time streams, add them together with the appropriate delays to mimic a dish that focuses in one part of the sky. And what you gain by that is that because digital time streams may be copied freely, you can just copy the time streams and add them together with different sets of delays to point the telescope, so to speak, in different directions. If you have enough computing power, the number of beams you can form, or the number of directions that you observe, n, sets the computational cost of the instrument. But you can just keep adding computational cost and scaling up by a large factor. So in CHIME, we have CHIME is sort of like, the idea is to take like the large n limit. We have a 4 by 256 array of antennas, and we can form all 1,024 beams on the sky in real time. So this is a statement that sounds too good to be true, I think, but it is true that in principle, we have the raw statistical power of 1,000 copies of the CHIME telescope, all staring in slightly different directions on the sky. The collecting area of CHIME is 80 meters by 80 meters, so that's a pretty good-sized telescope. The CHIME design is actually a compromise between optical and software focusing. Our antennas sit in these cylinders, which are these, which have a reasonably large collecting area. So the beam pattern that a single antenna would see due to the cylinder is focusing in one direction and is unfocused in the other direction. So the beam pattern on the sky of a single antenna, or the so-called primary beam of the interferometer, would be this strip. And then by copying different antennas, by digitizing antennas and combining them with appropriate delays, we can form software beams anywhere within that strip, a 4 by 256 array of software beams mimicking the 4 by 256 antenna pattern. And so this is the pattern of primary beam and software or formed beams. And CHIME has no moving parts. It just sits on the ground and stares. So this whole pattern of primary beam and formed beams rotates with the sky and sweeps out over 24 hours, sweeps out the whole sky, or at least the part of the sky in the northern hemisphere that we can see from the CHIME site. And so what CHIME produces every 24 hours is an image of the sky whose angular resolution is about 1/3 of a degree. That's set by the size of the formed beams. In the frequency range from 400 to 800 megahertz, which happens to be a very interesting frequency range for a lot of purposes. We can do cosmology via the 21 centimeter line in the redshift range 0.8 to 2.5, and also look for pulsars and fast radio bursts that are going to be the subject of this talk. So I want to show you the table. I forgot to say, I'm not really a radio astronomer. I'm a CMB cosmologist pretending to be a radio astronomer. So what got me interested in this project a few years ago was just thinking about this table. So this is way too simple, but it's qualitatively correct, I would say, that for many purposes, the statistical power of a radio telescope is proportional to its mapping speed, which is just the collecting area that sets the instantaneous sensitivity per beam, times the number of beams that the instrument can form, times some order 1 factors like system temperatures and bandwidths that I've omitted in this back of the envelope comparison. So in some weird arbitrary units, which aren't actually what's used, if I multiply collecting area times number of beams for some famous radio telescopes, then CHIME comes out comparable to or larger than the other telescopes on this list, including, say, FAST. But if you think about what this is saying, here are CHIME and FAST compared to scale. CHIME is a 500-meter telescope. It's one of the biggest and most expensive projects in astronomy. And CHIME is this little low-budget, well, we don't think of it that way, but by comparison, little grassroots effort in British Columbia. It just sounds too good to be true that these two instruments could ever have comparable statistical power. But then this calculation also seems too simple to be wrong. So what's going on? Yeah. So there is, you might be thinking that there's a catch here, and there is a catch. And I didn't realize what it was when I started working on this, or I might have chickened out. And maybe you know what it is already. But I'll say in a few, I called it a challenge, not a catch in the slides. And I'll say in a few slides, but first let's bask in the glory of some forecasts showing what we can do with this huge mapping speed. So for cosmology, via 21 centimeter intensity mapping, CHIME is an incredibly powerful instrument. These error bars on the expansion history, quantify our sensitivity compared to some current measurements of the expansion history via BAOs, barometric acoustic oscillations. The redshift range of CHIME, by the way, was chosen to cover the so-called redshift desert, where it's hard to measure BAOs with galaxies, but the quasars haven't really started yet. The Lyman alpha Force quasars come in at higher redshift. Fast radio bursts are an astrophysical mystery and a high-profile topic. Here's a picture of a fast radio burst. So very occasionally, a bright, short, and highly dispersed pulse of radio emission is observed. Highly dispersed means that the arrival time of the pulse is a function of the frequency channel in such a way that the delay is proportional to frequency to the -2. I forgot to say on the slide, but that exponent, frequency to the -2, that delay, is what's obtained by propagation through a thin, cold, unmagnetized plasma. So this is suggesting of free electrons. So this is suggesting a high electron column density between us and the event, possibly because the FRB is at a cosmological distance and it's propagating through a lot of IGM. The physical mechanism of these events is unknown, and explaining them has become one of the most interesting puzzles in astrophysics, maybe like GRBs 30 or 40 years ago. The field is largely statistics limited and sort of in a discovery mode. Only 30 FRBs have been discovered since the initial one in 2007. And the CHIME event rate, because of our mapping speed, I put ... for dramatic effect, is something like 10 per day. So when we can start this search, we should really be a game changer. More forecasts. So CHIME is potentially super powerful for searching for new pulsars. Pulsar science, just to review the history in like 5 bullet points, has been a really interesting and fertile area of astronomy. The first observational evidence for gravitational waves came indirectly through watching pulsar orbits decay. I think pulsar science can claim the first detection of extrasolar planets, although that may have been kind of a fluke. Some of our most precise tests of general relativity have come from studying pulsar systems. Of course, lots of new astrophysics, interesting systems like magnetars. The total number of pulsars that have been found so far is around 2,000. But the total predicted galactic population is something like 10 to the 5. So statistically speaking, this field is, there's still many, many discoveries to be made. And if we could search, if we could optimally search 30 days of CHIME data to its statistical limit, we would be able to find something like 4,500 new pulsars. It would be really amazing to find this number with one experiment. Now, I should say that in practice, the number that we find will probably be determined by how well we can compute, how well we can do that analysis. But the statistical potential is very, very high. Another thing we're trying to do with CHIME is detect gravity waves by doing precision timing of pulsars, or help detect gravity waves. So just like LIGO detects gravity waves by comparing light travel times between arms of an interferometer, if you observe a network of many pulsars in the galaxy and a gravity wave goes through, it advances some pulse arrival times and delays others. You infer the existence of the gravity wave. CHIME is, even though CHIME has very high mapping speed, CHIME's frequency range is not really in the sweet spot for observing pulsars. It would be better to be at higher frequencies. So at our frequency range, ISM propagation effects broaden pulses significantly and limit the precision of the timing. But when we combine CHIME with measurements at higher frequencies, we can improve the global timing solution by pinning down ISM-related nuisance parameters. And so we intend to contribute our pulsar timing measurements to nanograv, and we estimate that we can improve timings for most of the nanograv pulsars by a factor of 2 or so. So CHIME is interesting for pulsar timing, but it doesn't have the, amazing forecasts of the other things on this list.
Can you give estimates for rate of achievement, like just instead of monitoring, see like extremes and that, and so on that are seen in quasars, especially from time to time. Some intervening, unusually configured plasma screen that automatically.
Oh yeah, so that's a good thought. I'm not sure how to quantify it. I imagine that CHIME is very powerful, since we do observe every location on the sky every day. It would be very powerful.
One of the new projects that will be starting from the UCFI grant is to do like all sky monitoring, looking for extreme scattering events, flares, and outputs.
I think it's way off topic, but for ESEs, pulsars are the perfect source because they actually point like for all the ESEs that we talked about before, and time will monitor every node also in several hundred with overhead of time, which is all of magnitude more objects than ESEs that never gone after, and those won't have the confusion limits. So I think CHIME will, it'll be a complete game changer for the ESE field. And the only question is, how much is people to get excited about ESE? Actually, analyze all that data. I mean, just what's the light curve of 1 point a day for the objects and very modest size data space?
Well, that's the issue.
It's getting people to care, that's one issue.
Okay. So the challenge in all this is the following. So it is true, I concentrated on this column of the table, the mapping speed. And it is true that this more or less determines the statistical power of a radio telescope under the assumption of infinite computational power. But the computational cost of the analysis is proportional to this column, the number of beams, or the amount of data that the telescope generates. Or maybe worse, depending on what you're doing, it could be like a power of n beams. So what we've really done with CHIME is move difficulty from hardware to software. We're saying instead of building instead of getting our mapping speed compared with fast from large A and modest n, we have modest A and large n. So we're not going to face the hardware and fundraising challenge of building a 500-meter telescope. We're going to confront difficult problems in software instead. And the data rate of CHIME is something like 100 times the other telescopes in the list. And radio astronomy already, by reputation, is one of the most computationally intensive areas of astronomy. So scaling up by a factor of 100 is a really ambitious step in this idea of getting mapping speed from very large n. And it's not a priori totally obvious that this is a step in the right direction. So I want to talk a little bit about the CHIME computing, just to quantify and explain the challenges a little bit better. So the first thing that happens is that the electric field at each of the antennas goes through a bunch of custom FPGA boards, field programmable gate arrays, where the time streams are digitized and channelized into frequency channels. And the raw data rate at this point in the pipeline is 800 megabytes per second, or about 70 petabytes per day. I like to put this in astronomers' units by saying that it's 5,000 copies of the LSST telescope. So LSST is often quoted as being an example of big data in astronomy at 15 terabytes per day. Data rates in radio astronomy are much larger than, as far as I know, than other areas of astronomy.
The number that keep always throws around is 1 terabyte a second. Is that further upstream before the PGAs or something?
Oh, right, that's the same number. I mean, you must mean a gigabyte per second. Oh, I'm sorry, this is 800 gigabytes per second. It's wrong on the slide. It's wrong on the slide. Thanks. My slides are not debugged. All right. Then next up is the GPU correlator, which is most of our computing power. This is a 1024 GPU machine. That's a huge computer. This CHIME is one of the largest supercomputers in Canada. What the GPU actually computes is the 2-point correlation function on a per nanosecond basis between every pair of antennas in the telescope. At least that's computed in some GPU register for a few cycles somewhere. And then the GPU can form from that a bunch of smaller time streams which are sent downstream for further processing. If you're interested in cosmology, then you receive from the GPU, from the correlator over the network, the visibility matrices, which is a n antenna by n antenna matrix every 10 seconds. If you're interested in precision timing of 1 pulsar, you can ask the GPU correlator for the electric field at that 1 point on the sky on that 1 formed beam on like a per nanosecond. If you're interested in looking for FRBs, you can ask the correlator for the intensity, that is the electric field after squaring, time downsampling, and averaging over polarizations on, say, a 1 millisecond time scale at 1 point on the sky or even at every point on the sky. So the GPU correlator is sort of the first stop computing that computes and reduces the data for further processing. Yeah, we can look for FRBs in every beam all the time.
Well, it sounds like you have to correlate in different ways for different types of sources.
Yeah, so the FRB search, let's see, if I compare the FRB search to pulsar timing. To do precision pulsar timing, I need the maximum possible information at 1 point or a few points if I want to time multiple pulsars in parallel. That is, I need the full electric field every nanosecond. For the FRBs, I need less information. I can downsample to millisecond timescales, although I do need a bunch of frequency channels. I need some frequency resolution. So that's less information per beam, but I can afford, under a bandwidth constraint, to get that information at every point on the sky.
At the same time.
Oh, that's right. Yeah, these can all run in parallel. So then we have these purpose-built backends that are reducing the data further to an amount that we can transport off-site and analyze on conventional supercomputing facilities. And these are big machines, like the FRB backend. Well, we're in the process of building it, but when it is built, it'll be like a 2,000 core cluster.
On its side.
Yeah.
How you transmit it? Ship disks around, or you kind of do it
Yeah. So these, well, we have a bunch of file servers on site, but at some point we do want to send stuff off site, and we have to get it down to like a terabyte a day, or maybe 10 terabytes a day. Something of that size is feasible. Okay, so the CHIME hardware achieves incredible sensitivity at very low cost. But in order to actually translate that to science results, we have to solve some really hard computational problems. And according to my tastes and what's interesting, these are the 4 big computational problems that we need to solve. Real-time detection of FRBs, real-time flagging and removal of radio frequency interference or human-made radio transmissions from cell phones and other things. This is by far our biggest nuisance issue. The problem of searching for pulsars in real time or close to real time on computers on site. And for cosmology, separating galactic foregrounds from radio emission from synchrotron radiation in our galaxy from the cosmological signal, 21 centimeter line emission at cosmological distances. And so we've been in parallel with my colleagues that are always working very hard to build this hardware. We have been working on these algorithmic problems very hard for the last few years, and the talk is mainly going to be a status update on how we're doing. So the question of whether FAST and CHIME are equivalent, I think it's too simple to just say yes. The answer is maybe, or at least a few years ago, the answer was maybe. If we can solve some hard computing problems, maybe we can make this true. So I'm going to start by talking about the FRB search. So the FRB search, so after the intensity time stream has been formed at a bunch of beams on the sky, if we just restrict attention to one of those beams, then we would have the following computing problem. You have a computer that's receiving a two-dimensional array over the network, where the axes are time and a frequency channel. And an FRB would be, would be on a track like this at a signal to noise where it's hidden and not visible unless you can't be distinguished from noise unless you sum all of the array elements together along the track. So the FRB search problem is the problem of taking this continuously streaming array and forming all sums of this type where the total de-dispersion delay in CHIME can be tens of thousands of samples here. And there are also 16,000 frequency channels. And the data arrives at the rate of 1 sample per millisecond. And there are 1,000 of these beams to search, so it's a huge search. In the literature, there are two general strategies of algorithm for solving this problem. The slides are going to get a little computer sciencey. CHIME is really a computer science problem disguised as a physics problem. So one approach is direct search, where you just evaluate all these sums by brute force. And that has a computational cost proportional to TF squared, where T is the number of time samples and F is the number of frequency channels. And then there's something called de-dispersion, which I'll show a recursive algorithm that I'll show in cartoon form shortly, with computational cost TF log F. So at the level of big O analysis, this looks much better. It's for CHIME, F is of order 10 to the 4. So we'd expect tree de-dispersion to be like 1,000 times faster. But however, there are a few problems. Tree de-dispersion tends to underperform in practice due to memory bandwidth bottlenecks. And there is also, the question is continuously raised in the literature as to whether tree de-dispersion can really be statistically optimal. Let me just make those comments in advance, and now I'll actually tell you what tree de-dispersion is. So the first step is to regrid the y-axis of the array so that the y-axis is frequency to the -2 instead of frequency. So that the problem now becomes the problem of summing a two-dimensional array along all possible straight lines. I'm going to describe a scheme for doing this, which approximates each straight line by a jagged sum of samples. And the sums are built up recursively as follows. So in the first step in this tree algorithm, I'm going to take all of these. I've illustrated it for an 8-channel example. I'm going to take all of these channels in pairs, take these channels in pairs, and I'll form all blue sums, which are related to each other vertically, and all red sums, which are related to each other diagonally. And I'll put the blue sums in this child array and the red sums in this child array. So the color coding is supposed to help you keep track of how each single element in a child array comes from 2 or more elements in a parent array. So this blue guy in the child array is the sum of these 2 guys in the original array. And this red guy is the sum of these 2 things. Now I just do the same thing recursively with each of these child arrays. So to get grandchild arrays. So I've gone through this child array and taken all vertical sums and put them in the grandchild array, and formed all diagonal sums and put them in another grandchild array. And the color coding again indicates how, if I want to know how this grandchild was formed, it was the sum of these 2 guys in the child, and these 2 guys in turn were the sum of these guys in the parent, in the root. And in this 8-channel example, if I do one more iteration, I'm done. And the final great-grandchild arrays have formed all possible straight line sums in the original array. So the idea is just to recursively divide and conquer, to say that if I take another way of thinking about it is that I take the original array, I want to form all of these sums. I can do that by dividing it in half forming all straight line sums on the two halves independently, and then doing another pass where I combine, and so on recursively. It's a very natural idea, I think. So our code is optimized to death, and I want to explain what to death means by example. So here's a slide. The next two slides are for people who like writing code. I like writing code. So here's an ordinary C++ function to take the transpose of an array. I just have an array in row major order, and I want to write it out to a different area of memory in column major order. It probably seems like this is the only way of doing it, and there's no real obvious way that this code could be optimized. Here's a version that's 4 times faster. This code also takes the transpose of an n by n matrix. And the way that it works is that these functions are compiler intrinsics that map one-to-one onto assembly language instructions. In 2012, Intel introduced the AVX2 instruction set that has registers that hold, this is the only slide where I'm going to talk about this stuff, that have registers that hold 8 single precision floating points at once. And the fastest way to do a transpose is to read the array out in 8 by 8 submatrices and do the transpose in registers. These special instructions are swapping things around in registers so that you get 8 swaps for the cost of 1, so to speak. In one clock cycle, you can rearrange 8 things. This type of hand vectorized code, vectorization is the term for assembly language instructions that do 8 things at once. Surprisingly, it's very difficult for compilers to find. The compiler is, 4 times, if you just give the compiler this, it can't find this. But a human can. So we got, now normally, this is a huge amount of work, and it would probably be easier just to get 4 times of the computing time. But we're building these huge supercomputers from scratch, and to run the same code for 5 years, we can't just make them 4 times bigger. So we got, really experienced at this. And most of our low-level, inner loops are written like this, and they can run, well, depending on what you're doing, they may not be much faster, or they can be like up to 10 times faster. For sort of ordinary operations, like taking transposes of matrices. It really surprised me how many cycles you can squeeze out of the computer if you're really determined and you have a limited budget and you need to do a tremendous amount of computing. OK. A few more things I want to talk about in relation to treaty dispersion. So one is blocking the search. I used to have some slides that tried to diagram this, but I think they were not a success. I haven't found a good way of explaining it yet. But so let me just remark in a few bullet points that in a straightforward implementation of the tree algorithm that I described, the number of passes that you have to make over the array is equal to the log of the number of frequency channels. And that makes the limiting factor L3 cache bandwidth. In each of those processing passes, you have to exchange the data between DRAM and the L3 cache. It is a non-obvious fact that treaty dispersion can be modified to process the array in blocks so that the array only goes through L3 once, and there's a 2-pass algorithm. And this is a huge speed up, and in addition to the assembly language kernelization, is the reason why our code is so fast. So with these changes, the assembly language kernelization and this blocking trick, this type of blocking, by the way, is how Intel's linear algebra libraries are so fast. They put a lot of thought into figuring out, if you want to multiply 2 matrices, how to divide that operation up into cache-sized chunks. So our blocked assembly language kernelized tree code is 7 times faster than the best that we could do using ordinary civilian C++. And also scales nearly linearly to multiple cores because L3 cache bandwidth is an even bigger problem when you're trying to run in parallel on multiple cores because all the cores share the L3 cache. Another interesting property of this blocked algorithm that turned out to be really crucial for us is that it is incremental. The data can be processed incrementally in few-second chunks, and an FRB is detected within a few seconds of the trailing edge entering the telescope. Which is really useful. Our algorithm, I think, is the unique algorithm that has this incremental processing property. And that's really useful for real-time alerts. and also has an internal use because it's very useful to inform the correlator as quickly as possible when you detect an FRB, because the correlator in CHIME is buffering the raw voltages, and we want to save those to disk if we can. So this is a technical point, but it's really important for us. And then finally, when I talk to radio astronomers, the question always comes up over whether tree dispersion is really statistically optimal. And I had this conversation so many times that I reduced the answer to like the form of a theorem. So if you do the following, there's an initial regridding step where you change the data from being channelized in an array which is equally spaced in frequency to one which is equally spaced in frequency to the -2. And if you do that initial step by smearing, each frequency channel in the raw data occupies some non-integer number of frequency to the -2 channels. And if you assign them with equal weight or partial weight, and if you upsample the tree in time relative to the data, then in the limit, then tree dispersion becomes statistically optimal. In the limit where you use a large number of tree channels and a modest upsampling factor, then dispersion is a perfectly matched filter. And you could see this, we have some Monte Carlo simulations where we change these parameters. We increase the number of frequency to the -2 channels in the tree and the upsampling factor of the tree, and the fraction of the signal to noise that we recover goes to 1. In summary, we wrote this really high-tech FRB search code, which is provably near optimal. We have a theorem that it's recovering close to 100% of the signal to noise. It runs in real time with this like really low latency that we actually didn't expect to get when we started, the latency of a few seconds. And it's much faster due to all of our low-level optimization than existing search software. And here's one way of quantifying that. CHIME is the world's largest FRB search in data volume by a factor of 1,700. The second largest search, as far as I know, is ASCAP, a 36-beam search. And with the ASCAP parameters, as I understand them, which are in this corner, we could process the ASCAP survey in real time on like half a core of this laptop. Like same cost as like watching a YouTube video. So they use GPUs. The question of whether CHIME and FAST are equivalent, I think for FRBs, the answer is just an unqualified yes. We just totally crushed the FRB search problem. I'm going to talk about our other, I'm running out of time. I think I have too many slides.
Quick question. So once you think you detected an FRB, you can modify the data collection so that you basically get the full electric field information.
Oh, yeah. So I forgot to say about the FRBs that the way we do the FRB search is that it's like a triggered search. This 2000 core backend is just triggering. It just generates an event when an FRB is seen. And then the data is buffering. The intensity data is buffering here. And the electric field data is buffering back here. And when we trigger, what we do is we just trigger a saving the event to disk. Then we can transport it offsite or post-process it arbitrarily.
So when you practice what fraction of FRB would you catch?
Oh yeah, so like a normal FRB with a DM of, the answer is that we can buffer about 60 seconds of data here, of electric field data. And we can buffer about 5 minutes of data here. And then we trigger right away with a few seconds. So normal FRB at a DM of 1,000, that would be 20 seconds of dispersion across our band. So we would comfortably be able to catch the whole event and write it to disk. But if we ever encountered a DM 10,000 FRB, we might be in some more intermediate situation.
If you get an expected rate of 2 FRBs a day, the goal is not to write all 2 hours because the dump is on the terabytes of dumping, so the problem is probably would only write maybe 1 a day max, 1 to 10. I think that kind of people have 1 to 10 might actually be more than they fully execute.
I mean, I think we could buffer them. I think we could dump them all. We'd probably.
With this speed, you have to write with this.
Are you going
Like-
also going to do on the fly?
Sorry?
On the fly, looking
On the fly, no, because the actually that we have some technical limitations to implement. We can only do that's a good question because the magnetic field analysis is really interesting. Yeah, I agree. So this back end only gets the intensity data, that is after averaging over polarizations. So the only way we would be able, in our setup, currently at least, the only way that we could do a rotation measure analysis would be if we, sent the trigger back to the GPU correlator, which is buffering the electric field data, and got that data to disk.
Of course, you're going to discover more repeated, so then the game changes when you just go wrong.
Yeah. So if we do,
I'm sure you will.
I hope so. That would be really exciting.
But do you think it's important that we get rotation measures for every FRB? We should speak to the important people like Kendrick and Ryan at the moment who have input on whether we get rotation measures for every FRB. It's a spec which is not in the pipeline right now. It's not part of the spec. You could build it and find just software. It's a software problem that will have to be implemented. It's not there's no hardware needed to deploy.
Yeah, we could change some things. I mean, so right now the reason that we have trouble is that, this gets tricky, is that the FRB backend only receives intensity, not polarization. But we could receive both polarizations. We would just need to pay, in order to satisfy a total bandwidth constraint, we would just need to, say, receive 1/3 of the frequency channels. If we were, instead of receiving just I, receiving I, Q, and U, we'd need, yeah. Your question about rotation measure is something that I think we're still figuring out ourselves. Okay. So the next problem I want to talk about is the problem of removing RFI, or radio frequency interference, in real time. When I give talks, I mostly talk about math and algorithms, and so it may seem like I spend 100% of my time doing this, but I made this chart of how I actually spend my time. And by far the hardest problem, where most of our time has gone in CHIME, is dealing with RFI. It's just a much harder problem than I originally anticipated. So the largest instrumental effect in CHIME is radio frequency interference, or human-made radio transmissions. In CHIME, our main tool, we have more than one line of defense against RFI, but our main line of defense, and the one that I'm going to talk about, is just masking the data masking outliers in the time and frequency plane before we do de-dispersion. So this is a complex problem that requires a lot of telescope-dependent tuning of software. And so every experiment, unfortunately, tends to write their own RFI masking code from scratch. And it's sort of an open problem whether we'll one day have a good general solution to the RFI removal problem. And I would like to speculate a bit on what such a general solution might look like. Here's the CHIME FRB pipeline in action. And since this is the first time I've showed CHIME data, I'll talk about it a little bit. The top panel is just raw intensity data from the telescope. And you can see, some parts of it are a lot noisier than others. The black stripes here are data that didn't arrive. In this case, because we were doing an engineering run, and some of the correlator nodes were not running. So there are a lot of frequency channels here that are just missing, and they're black stripes. But the ones that are not missing, you can see, some of them are purple, which means that there's not much power there. And some of them have blue and red structure all over the place. All of that structure that you see in the raw data is RFI. Like this up here is a cell phone band that is just totally saturating the plot. This is the data after processing by our RFI removal pipeline, and it's just masked a bunch of the data. So it's decided to just mask a lot of frequency channels here, and they're all black. And then there were some intervals of time that it didn't like. You can see some black stripes running up here. And also just some general irregular masking. Like there's, this frequency channel is, it's happy with some of the time, and some of the time it masks it. And this array, this masked array, so in this array, after all of our masking, and this masking happens in real time, and I'll talk about how we do it in a minute. So after we do this masking, you can't see any RFI. The plot scale here is much lower. And all of the fuzz that you see in this plot, as far as I know, really is like thermal noise. So this array, this masked array, is what we actually apply our de-dispersion to. And this plot is actually an output of the de-dispersion, where now the axes are time and the dispersion delay of the pulse that was summed over in the de-dispersion part of the code. And you can see that there is this sequence of blips is a pulsar, in this case the BO329 pulsar, which is too faint to be seen by eye in this plot, but pops out after you do the de-dispersion. And I chose an example where we do get, so these pulses are all at the same dispersion measure or dispersion delay because it's the same object, the same pulsar, propagating through the same column density of electrons, but it's going off at a bunch of different times. And I chose an example where we did get a false positive from RFI. This event up here, which is at a different dispersion delay. It's not an FRB, unfortunately. It's a false positive because there's a little bit of uncleaned RFI in this plot. But you couldn't tell by eye. There's nothing like visually here that you can point to that's responsible for this. OK. So the key computational step here is this masking. And I want to show, I forgot I was going to show one more plot. I consider this plot to be like our RFI victory plot. And I really think that this is one of our main accomplishments in the project. This is actually the very first time we were able to turn full CHIME on and feed its data through the FRB pipeline over a long contiguous acquisition. This is about 2 days of data. And what's shown in the plot on the y-axis is the signal to noise of the most significant pulse, if any, that the FRB pipeline found. So when the BO329 pulsar goes through the beam every 24 hours, the FRB pipeline sees those pulses and detects, 30 sigma, 35 sigma events. And likewise for the giant pulses from the crab. These are the only pulsars that are bright enough. This was an early engineering acquisition where we didn't have much sensitivity yet. These are the only 2 pulsars that are bright enough to be seen. The other pulses in the plot are all false positives from RFI. So like here, there's a 12 sigma or so false positive. But this is an incredibly low false positive rate. Like a more typical rate would be like a few events per hour. We don't have, as far as I know, we've never gotten a false positive in our pipeline, an RFI false positive above 15 sigma. I could be wrong about that, but I don't think we've had anything above 15 sigma yet. And we occasionally, if you put a cutoff like 10 sigma, we just get a few false positives per day. And compared to other projects, that is an extremely low false positive rate. And the way that our software works is as follows. So it has to be really fast. The computational speed requirements are as stringent as the de-dispersion pipeline. So everything kind of has to be like assembly language kernelized and optimized to death. And what we do is we write highly optimized chunks of code which are interfaced as transforms. So you can take a transform and apply it to the data and the mask, which are continuously streaming arrays. And we have a library that allows you to chain together transforms. And then as we think of ingredients to add to our RFI removal scheme, we define new transforms. So we have transforms that clip intensity outliers at different thresholds, possibly with different levels of smoothing. Clippers that are transforms that mask data based on the variance of the intensity array. If we see part of the data where the noise looks like it's flaring up, we can mask it. There are a bunch of different detrending type transforms that try to estimate baselines and subtract them. We can upsample and downsample the data, take it down to a different resolution and run some more transforms, then upsample again. A whole library of possibilities. And these are all written in assembly language, but we have a Python framework for experimenting with them. So you can write Python code that treats these assembly language routines as blobs and chain them together efficiently so that you don't have to be some like assembly language Jedi to experiment. So as CHIME has progressed, we've tried different possibilities, and we've evolved our RFI removal strategy. And our current strategy consists, it's highly iterative, and it consists of like 100 different transforms. This whole chain of 100 transforms needs about half a CPU core to process the CHIME beam in real time, which is an acceptable cost. But finding this sequence of 100 transforms really required a heroic amount of human time experimenting on archival data. This was mostly led by my student, Masood. So I would like to speculate. So this has worked, and this victory plot is supposed to be the proof, this approach. And so I would like to speculate that this is a very promising general approach to the problem of removing RFI from radio astronomy data. And I would like to propose that there could be some master toolkit of transforms, which are not too dependent on the telescope. But then, because every telescope operates in a different RFI environment, the part that's different is the order, the ones that are useful in the order in which they are chained together. So if the dust settles on CHIME and we can stop putting out fires, something that we would like to do is to try to come up with some sort of learning algorithm that so that a human doesn't have to do it. Instead of having a human spend a huge amount of time experimenting with different orderings of transforms, different possibilities, you could just point a learning algorithm at a bunch of archival data, throw a bunch of CPU hours at it, and come back later, and it would give you the transform chain. So this, I would speculate, is the form that a general solution to the RFI removal problem is likely to take. And if you wanted to do something that would be non-glamorous, but of immense practical importance in radio astronomy, it's hard to think of something that would have more practical importance than this. So this is something that right now we're just putting out fires trying to get CHIME to work. The CHIME RFI removal, the CHIME specific part of this is working very well. But we would like to come back later and work on this because it seems like a really interesting direction. OK. So the real-time RFI removal, which is really a prerequisite for having this work, is also working. And the timing actually seems to be working on this talk, which is kind of, I thought I had way too many slides. So in the last 10 minutes, I'll just present a few slides with some initial thoughts on searching for pulsars. The CHIME Pulsar Search, we would also like to search for new pulsars in real time with CHIME. And this is roughly where the FRB search was a few years ago. We have some forecasts that look amazing, basically no software written, and big computational challenges that we still need to solve. I published a methods paper a year and a half ago proposing some new algorithms, which is what I'm going to talk about in the next few slides. The forecasts look amazing, and we estimate that an optimal search of a month of CHIME data would find like 4,500 new pulsars. And over the summer, we're hoping to do a lot of code development and see how close we can come to hitting this target. And thanks to Brian, who's meditating. It's a fascinating talk. We have funding for a Pulsar Search backend. So if we can get the software to work, we can build the computers. So I'll just show a few slides to show the sorts of things that we're thinking about. The Pulsar Search problem is the problem of searching for a quasi-periodic sequence of pulses in a noisy time stream. And the simplest case would be, just to start with the simplest case, a constant period search where the pulsar is perfectly periodic and the pulse rate is not slowing down or speeding up with time. So that the only parameters are the pulse frequency, and then there's also a phase parameter at a fixed frequency. The pulses there's a periodic parameter that tells you where the pulses are actually located. So even in this rather trivial parameter space, I think one could still make interesting new statements. So the optimal search algorithm, I like to start with sometimes when I think about computational problems by thinking about what you would do if you had infinite computing power. If you're searching for a periodic sequence of pulses of this type with an unknown pulse frequency and phase parameter, then the optimal thing to do would just be to loop over every pulse frequency and phase, and then for every such pair of trial parameters, just integrate the data times the trial signal. So this is sometimes called trial folding, where you just fold the data periodically at every possible frequency and phase. This is too slow doing this. If you implemented this by brute force, literally outer looping over every parameter and then doing this integral or sum, this would be too slow. But there's this fast algorithm, and as far as I know, this is new. I pointed it out in this paper, and I think it's really surprising that it wasn't noticed. So what I want to do is just interpret trial folding as an integral transform. So it is an integral transform. I have an operation where I put in a function of one variable or a 1D array, and I get out another function of two variables or a 2D array. And it's defined by an integral for every possible value of these parameters. I do an integral over the original data. So that looks like, kind of like an FFT or something. And I claim that viewed as an integral transform, this operation factors as a sequence of Fourier transforms, which can be done quickly using the FFT algorithm. And this can be worked out in like 5 lines of algebra. So in this slide, I like this slide because it shows that if you just find the right 5 lines of algebra, sometimes you can do something really new and interesting. It's kind of surprising that's true, but it is. So in each of these steps, I've done something, just one step. Like in this step, I've taken the pulse profile, the function rho of t here, or rho of phi, is supposed to be some narrow periodic pulse. And Fourier expanded it. In this step, I've done an integral. In this step, I've reversed the order of summation. And the result is something that can be evaluated quickly using some FFTs. This sum is an FFT. There's an interpolation step that's kind of hidden here, and then another outer sum, which is also an FFT. And you can just compute using this final form of the output of the transform. You can just compute this integral for all omega and phi at once efficiently, the same way that the FFT computes the Fourier transforms at all frequencies at once efficiently. So that's something interesting to say just in the trivial case of a constant period pulsar. I think this is the right way to do the analysis. Generalizing to more complicated search spaces, the next thing you might look for is a constant acceleration pulsar. So this is a pulsar where the frequency is no longer constant, but the pulse frequency is increasing linearly with time. So that the integral transform looks like this. There's an acceleration term that looks like alpha t squared, where alpha is a new parameter in the search space. This search can also be done efficiently using a tree algorithm. If you look at this integral transform, then the size of the search space is going up as the time stream size cubed. If I double the length of the time stream, then I need to search twice the number of trial frequencies, and it turns out 4 times the number of trial accelerations. That's really all you need from that fact alone. You can see that this can be done quickly with a tree algorithm. If you just imagine dividing your time stream in half and recursively computing this output on each of the halves, then because it's an integral, each array element for the big time stream is a sum of an array element in the first half plus the sum of an element in the other half. At the leaves of the tree, where the number of trial accelerations is 1, you have the case of the constant period search, which is done by the previous algorithm. So you can see from this that as you go up the tree, the computational cost of filling in this array, each array element is just the sum of 2 things. So the computational cost of filling this array is just the size of the number of elements in the array itself. Because this is the sum of the computational cost of every node in the tree, because it's a geometric series, it converges. So this is a fast algorithm. I claim faster than what's usually done for searching this space where the total computational cost is just the number of triples of trial parameters that you eventually intend to search. So this is the fastest possible algorithm for an exhaustive search that exhausts all possibilities. So at the level of big O analysis, this looks like the right way to do a constant acceleration search, the best algorithm. What we hope to do next is more study to see, for example, whether it can be implemented efficiently on a GPU, or whether it's significantly more optimal than other methods, which are faster and approximate. They don't get 100% of the signal to noise. I don't think I've ever given a talk before where I ended up with more time than I expected. I didn't actually think I would get to these slides. So there are more. So in these slides, I've talked about a constant frequency search and a constant acceleration search. In this paper, I go on to talk about other possibilities. But I think these possibilities are enough to like convey the flavor of the subject, the sorts of things that we're thinking about, and why we think we can improve. Over the summer, we're hoping to make a lot of progress on this. In conclusion, I think we are making great progress on solving these hard data analysis problems that we need to solve to scale radio astronomy up to the CHIME volume and for CHIME to fulfill its potential. These were, at one point in the talk, I defined these problems. The problems of real-time FRB detection and RFI removal are basically working, although we'll undoubtedly continue to refine that software as the experiment progresses. I don't see how there could be any showstoppers at this point. The real-time pulsar search is in an early stage and is in progress. Cosmology, I just didn't talk about at all in this talk, but other people in CHIME are working very hard on this and have made a lot of interesting progress. It's just a subject for another talk. And we have high hopes, given the progress that we're making for what we might be able to do with CHIME in the next few years. So for some problems, like finding FRBs, it really is true, as far as I can tell, that CHIME is the most powerful telescope on this list. It is also, by far, the least expensive telescope on the list. Its cost is a tiny fraction of these other experiments. Furthermore, it's really interesting to think about the future. CHIME can be scaled up. You could build something with 10 times the mapping speed or even 100 times the mapping speed on a budget which is not crazy for what big projects cost nowadays. So it's really fun to think about the work we're doing, not just as exciting for CHIME, but exciting for radio astronomy in general. In the last few years, I've really become an evangelist for the future of radio astronomy being large N and clever algorithms. Thanks.
I think a couple questions about fluxes. What will your flux sensitivity be for FRB when you have the experiment working as you hope to have it working?
Oh, you want a number?
Like Jansky milliseconds.
Oh, I don't know that off the top of my head. I should know that number. I don't know it off the top of my head.
Do you have a sense for how close, how far you are? Are you still order of magnitude away from where you need to be, or?
I mean, that is mostly a matter of collecting area. So we would be comparable to, Parkes or Green Bank. Is the qualitative answer. The big uncertainty, if you want to convert that to an event rate, the big uncertainty for us is that most of the FRBs have been detected at 1.4 gigahertz. There have been a few detections at like 800 megahertz.
Do you have a sense of what the sensitivity will be?
It can take about 1 tenth millisecond, which is not as Kendrick is saying, it's optically the whiteness of our vaccine and optical whiteness.
Later question is, if you say monitoring known radio sources, what plus are you going to get down to for known radio
The
sources?
nominal thermal limit per day is 50 microjackets.
Okay.
And we know whether everyone, but many number of the number of sources that flux limit is hundreds aesthetically and confusion limit is. From the dependability, we would be offered by this. So the one metric that CHIME does not do well on, it's just a fast telescope altogether survey, like FRBs or anything. But it's confusion that is, so you could continue to source apart. And that's the varying time.
You didn't mention it, but I double checked at the Pathfinder. Was any of that data recorded
Not enough. For technical reasons, we didn't. In the Pathfinder, we recorded a lot of incoherent beam data, where you average over the whole primary beam rather than beamforming at a particular point on the sky. And that was very useful for developing our RFI removal code. Like our RFI removal code was mostly developed on incoherent beam Pathfinder data. And then we were very pleasantly surprised to run for the first time in full CHIME and get these nice results. But the incoherent beam is not very sensitive to FRBs. So we did search about a month of Pathfinder incoherent beam data and didn't detect any FRBs. And that was actually an interesting upper limit on models that have a long tail to the flux distribution. But given what we were able to, the software that we were able to write for during the lifetime of Pathfinder, we couldn't really do a full-blown FRB search.
One more question. Yeah, your forecast for pulsar detect. So will we be able to detect any millisecond pulsars?
Oh yeah, those are all slow pulsars.
Okay. So are you doing it in the millisecond intensity stream or something like that?
That's right. Yeah, that's right. Yeah, detecting millisecond pulsars, a blind search for millisecond pulsars would be really tough. I don't know if I tend to be like a computing optimist, but that's a lot of optimism.
All right, well, send Kendrick again.